Before we get started on identifying compounds as molecular or ionic, I want to remind you that it's a great idea to work back and forth between Module 1 and this module. You'll need to have a great idea of how the periodic table is arranged, including the groupings that the chemist uses on that table. If you've had a solid chemistry course before, you can probably keep going on this section page without much issue. But if your background is weaker, I suggest you work through section 1.2, which discusses the periodic table in detail before you tackle this one. Also, I've prepared note-taking worksheets that follow the content pages in the course. These are optional and they're simply for your benefit, but if you're unsure of what you should be notating as I go along, these are a great place to start. Note that the best students will combine the content from these lecture videos with the content from the practice videos, images, and text. Those, along with the in-class practice, recitation work, and any extra practice present in any form in any module, is all free game for your quizzes. Chemists tend to lump compounds and elements into groups based on their properties and/or the types of atoms that make up those compounds. There are actually a lot of these groups, like a lot, but fortunately, you'll be responsible for naming compounds from just two of them. The first are covalent compounds, which are also called molecular or molecules, and the second are ionic compounds. As you can see from the chart, ionic and molecular compounds have very different properties because their bonding models are very different. You're not responsible for memorizing or even recalling this chart. It's shown to illustrate the importance of us dividing these two groups of compounds up. As I mentioned, there are other groups and therefore other nomenclature schemes that we could learn, but these two groupings are often thought of as the two most general ways atoms come together, so they'll get us as far as we need to go in Gen Chem. Most of the many groups I mentioned are actually just subgroups of these two anyway. Our covalent compounds occur when atoms that have an affinity for sharing electrons get close enough, but not too close, together. We'll go more into the detail of the energetics of bond formation later in the course, but for now, know that covalent bonds involve a sharing of electrons between two nuclei. Both of the atoms in the pair have to agree to that sharing, so they have to be similar enough in character. Our covalent bonds are generally formed between nonmetal elements for this reason, because they are similar enough in character. Once two atoms are involved in a covalent bond, the electrons between them don't belong to either atom anymore. They're shared between. Ionic bonds differ in that there isn't a sharing of electrons, there is a transfer of them. One piece that participates in the ionic interaction really wants to donate electrons, and the other piece that participates in the ionic interaction really wants to accept those same electrons. The electrons are not shared here. They are transferred from one species, referred to as an ion, to another ion of opposite charge. We'll discuss ions and ionic compounds in section N.2. This is a great first time to say that our bonding and therefore nomenclature rules are built on models. Our atoms are teeny tiny, making them hard to study, and therefore a number of the things that we will learn this term are going to be built on really good theory. Most scientists recognize that a model will have flaws. The fewer the flaws, the more elegant, but the use of models always introduces both error and variation. While you're wandering around the internet looking for additional resources, you might run into content creators from different theoretical camps than me. Keep in mind that I write your quizzes and I grade your assessments, so you should focus on the models and the theories introduced in the course content. The use of these two bonding models is representative of how we sometimes simplify the world through the use of our models. We create them so that they can describe boundary conditions, but we recognize that the reality is somewhere in the middle. And so we apply the most appropriate model to the situation, knowing that the other description might also contribute to the characteristics of our system. For instance, these classifications you are going to have to make are based on the concept of electronegativity, which is a different model. Here we took one idea, the fact that atoms come together to form compounds, and we combined it with another idea, that some atoms tend to have more of an affinity for electrons than other atoms. You will also be expected to synthesize models and ideas in this way. Technically, there is not a molecular bonding model. The bonding model is properly called a covalent bonding model. Compounds possessing characteristics of the covalent bonding model are referred to as either molecular or covalent a lot of the time, though. Many chemists will use these terms interchangeably. Also, there technically is not an ionic bond because there's that transfer of charge and not a sharing of it. So no actual bond, just an interaction. As a first exercise, pause the video in a sec so that you can review these chemical formulas. Now try not to feel silly while you follow along with Virtual Dr. E. The best students will, and it'll help them improve. While you're reviewing the formulas, determine whether the different formulas are classified based on the number of each type of atom. Try locating the elements on the periodic table to see if there is common ground between where they came from. And see if you can write a rule prior to my showing you how to do this. Now, pause the video now and give it a try. Again, historically, students that play along with the do-it-yourself parts of the course are more likely to be successful. Your first job is to be able to identify a chemical formula as belonging to either an ionic or a molecular compound. This distinction is important because, as we've seen, an ionic compound involves a transfer of electrons between ions, and a covalent compound involves the sharing of electrons within bonds. We will do this compound type identification by locating the elements that make up the compound on our periodic table. I suspect a number of you are saying, really, she's starting the whole college level chemistry course with water. And yes, I am, because it lets me point out a number of things with something that's at least a little familiar to everyone. First, it actually might not be water. There's no state of matter listed, and I'm not sure what the temperature is. So I don't know if this is steam, water, or ice. Those three terms define this one chemical formula in its different states of matter and really aren't as interchangeable as everyone makes them out to be. Is this nitpicky? Absolutely. Would you lose points on a nomenclature quiz for simply calling this water? Also, yes. Chemistry is a very specific and precise science. Change an enormous chemical formula by one tiny atom and you have something new and different with new and different properties. The beginning of this course is a great time to get in that mindset of close enough is not good enough. The minutia will matter here, and you'll be responsible for learning a lot of that minutia. Another very important thing to note is that hydrogen is found on the top of the column to the far left of the periodic table. In section N.2, when we talk about ions, it will make sense why it's placed here. But based on this same conversation we'll have, hydrogen could also be placed to the right of helium. Now, why would I move hydrogen to the right side of the table? Because our table is pretty neatly divided into nonmetals, shaded here with this blue triangle, and metals, which are all of the elements not shaded here with this blue triangle. Covalent compounds are formed between two or more of these non-metal elements. Now that we know that covalent bonds are formed between non-metal elements, let's talk about the actual bonding. Non-metal elements are able to share electrons with one another. When they come together to form compounds, they do so by sharing their outermost electrons and forming a chemical bond. Now we're going to look closer at the elements that make up H2O, but before I do, I want to remind you that there are a lot of things at the beginning of a chemistry course that might not make sense to you yet, and that's going to be perfectly okay. You're not alone. I'm about to show you the Lewis dot structures for these elements, but we'll prepare and talk about valence electrons and actually work with Lewis dot structures in Module 6. So you absolutely should not panic if you can't make these on your own. Focus on what the structures illustrate, which is the sharing of electrons, and not on the structures themselves. First, we'll have two hydrogen atoms in our formula. Because I've done this chemistry thing before, I know that each of these hydrogen atoms can bring a single electron in their outer shell, which is represented by this white dot. Again, focus on the hydrogen and the electron it can donate, and not why one dot is on the top right and the other is on the bottom left. They're placed where they are for a reason, but these diagrams are human constructs forced on an atom too small for us to see. So they're really just theoretical. We'll also have a single oxygen atom that brings 6 electrons along with it. Again, knowing why there are 6 electrons is not important right now. What is important and will really help with ionic nomenclature is knowing that most of our atoms like to have 8 electrons around them. They form the ions they do largely because of this rule, which is called the octet rule. When we draw our Lewis structures in Module 6, we will rely on the octet rule to figure out what our molecules might look like. Hydrogen's an exception to this rule, as it will only ever have 2 electrons around it, as that's all its single little energy level will allow it to hold. More on that in Module 5. Oxygen's electrons are 2 different colors here as a grossly oversimplified visual to show that some of oxygen's electrons belong to the oxygen itself, and these are the red dots, and some of oxygen's electrons belong to the molecule and can be shared, and these are the white dots. When these 3 atoms come together to form a compound, the atoms in the molecule. This sharing forms a bond, which is specifically called a molecular bond or a covalent bond. These 2 terms are going to be used interchangeably in the course, even if they probably really shouldn't be. There are 2 chemical bonds illustrated here, each sharing 2 white electrons, or the 2 dots inside the yellow ovals. These illustrate a chemical bond, which is the force that's going to keep this water molecule together. Because this is a molecule and these electrons are shared, it takes a fair amount of energy to get these apart from one another, which makes our H2O molecule pretty stable. The electrons that are the same color as the oxygen aren't involved in bonding. They're localized on that oxygen atom. Know that this sharing doesn't have to be even, and it definitely isn't here. As we get further into the class, it'll be important to recall that some atoms like to have electrons around them more than others. Oxygen is a bit of a ball hog. He's that guy on your 6U soccer team that wouldn't pass to anybody. The other kids, which are the hydrogen atoms here, had some interactions with the ball, but the oxygen was the star. So to wrap this first part up, since hydrogen and oxygen can both be found on the nonmetal section of the periodic table, they're able to share electrons with one another and will therefore form a covalent bond and thus a molecule. We will need to use molecular compound rules when naming this molecule, which we'll see in a bit. We've used H2O, but any 2 nonmetal atoms can come together to form a molecular bond and therefore a molecule. I've added some additional examples here. If you look up all of these atoms on the periodic table, you'll see that they all lie under this blue triangle and are therefore nonmetals. Some closing notes on identifying molecular compounds. First, the first 3 examples here, H2O, Pi3, and XeF4, are examples of binary molecular compounds. This is the family that we will learn rules for in a later subsection. Binary means 2 types of elements here. While we could have an actual binary compound in both atom type and atom count, such as NO, more often than not, our binary compounds will have a total atom count greater than 2. I've given the atom counts here. We'll do more with chemical formulas in the next subsection, but for now, see if you can come up with the same values that I have here for these atom counts. The last compound here, CHCl3, is not considered binary because there are 3 different types of atoms in its formula. You wouldn't be expected to name this compound for this course, as it uses a different set of rules than you'll be responsible for. But you would be responsible for knowing that it is a molecular or covalent compound and not an ionic one because all of its elements fall under this nonmetal triangle. Lastly, we have quite a few of our nonmetal elements that come together in different ratios, such as NO, NO2, N2O, N2O4, etc. All of these are molecules, and they all have different properties. You'll have to be able to identify both where the atom is on the periodic table and how many of that atom are included in the formula before you can name it, but we'll see more in a later subsection. So what happens if you have a chemical formula that has an atom outside of this blue triangle? Then, super simply put, you don't have a molecule anymore. When looking at the atoms in this formula, the oxygen is still in the nonmetal area because our elements aren't going to move from one spot to another on the periodic table. But the sodiums included in this formula are nowhere near that blue triangle. Instead, they're considered metals, which are all of the elements that aren't under that triangle. When metals and nonmetals come together, they do so oh so very specifically. Unlike some of our nonmetal elements that can come together in different ratios to give us different compounds, there's one and only one possible formula for compounds that include both metals and nonmetals. That's because there aren't atoms coming together to form bonds here like we saw with the molecular compounds. There are ions with specific charges coming together to form an electrostatic attraction. That's fancy speak for transferring electrons. You'll be able to determine how many ions are necessary for your compound by the end of section N.2. Your job right now is to identify the compound's type. As an extra example, here are a series of chloride salts. The term salt doesn't just refer to the table salt that you use to cook. It's a generic chemistry term used to describe any ionic compound. The chloride is universal to all of these examples. It's found under our triangle, so it's an example of a nonmetal element. The metals from each of the compounds are found over on the other side of the table, though. Not all of these are what we commonly thought of as metals in their elemental form. The sodium, given the symbol Na, is soft and you can cut it with a butter knife, for instance. It also catches on fire if you don't store it under oil. Barium, or Ba, and lanthanum, La, are also soft and malleable. Iron, Fe, is the stereotypical general population metal, hard, able to form into shapes, but only at high temperatures because it has to be melted first. But they're all considered metals, and therefore would be named using the appropriate ionic nomenclature rules. There are many more metals than nonmetals on our periodic table. The main task for this subsection is for you to identify whether a compound is ionic or molecular so that you can then name it. This video has walked you through locating the elements on the periodic table and going from there to identifying the compound type. Additional information, including a flowchart to use while you're practicing, is provided in the text that follows this video. There are also some practice problems that focus only on the content in this subsection, so you know that you've mastered it before you move on to the next one. To determine the type of compound you have, first, locate the elements that the formula contains on the periodic table. If the compound contains only nonmetals or contains only elements up and to the right of the stairstep, then your compound is a covalent compound. It will exhibit molecular bonding, which is a sharing of electrons. If your compound contains a metal element, which are found down and to the left of the stairstep, along with one or more nonmetal elements, then your compound is ionic. Here, there is less of a bond and more of just an attraction between two or more ions of opposite charge.